This is the lecture 2. We finished the lecture 1, and let's go to continue for the second hour. The next subject is universal Turing machines. So let's change gear a little bit, get into more tools so that I can understand better. Before we talk about more, like introduction, the purpose, motivations. And we are familiar with agent. What's agent? Agent is something sense and act. We are also familiar with the finite automata, all right? Finite automata over here, it's like you have FA is typically used in computer science. In electrical engineering, typically it's called finite-state machine. So we have a state. And what's a state? State, the context of input stream, typically not output, right? Suppose I have a state like ABC, they have input of the 0 or 1 in this case. Then depends on the state, depends on the input, you have two symbols, state and symbols. Then you decide which state to get into, right? Over here, the output is only actions, not accepting yet. Double circle means accepting, not accepting yet, not accepting yet, accepted, right? So all such kind of strings start means any number, including 0, all right? And vertical bar means all. And parentheses and put these two together. Star means any pieces of this, all right? And so M1 in this case, M2 like this. Do you see that? And you may combine different state together and build more competent machines. So the output for FA is accept or not accept. And agent FA that I invented is that you need to output a state, all right? So output is not just accepting, not accepting, but rather out the state. Other parts are the same so that many people understand the tool, so we can understand more complex things. So we build on our knowledge of symbolic school, and now we have a little new change, which is agent FA. In other words, the state included in the output. The action is part of the state, not just accepting, not accepting. The state is the output. So the action is a part of state. Remember, very important. The action is a part of state, and both are parts of output. This is very important because state need to be observable. We have a hidden Markov model, which is bad, I think, very, very bad. Hidden Markov model, very bad. They have local minima problem and learning extremely slowly. And a human, our action is observable. Observable. All our actions are observable. Then our state are vocalizable. Our state can be, you can ask me a question, I can explain to you using my language. So what I saw, my thought can be explained in language. So our action can be explained into the language. That's why the agent FA, all right? This is not as rich as the brain yet, but we build on our theory, all right? We build our mechanism. So attentive agent FA has a background, and you have multiple objects. Before agent FA has only monolithic input, 0, 1 give example, no background, no multiple object. Here we have multiple object in the input, and the theorem one said that attentive FA for the theorem is the control of a Turing machine is not only an agent FA, but also an attentive agent FA. In other words, that if you have a Turing machine, then the control is not just FA, monolithic input, in previous case 0 or 1, but rather it is an attentive FA. Because why? Because the Turing machine has a read-write head that can scan the input symbol And although it can attend only one symbol at a time, but it can aggregate multiple symbols into a single one using state. So that's why the idea behind the theory one is that if you have Turing machine, it's attentive, although it's everything is programmed. And so let's look at the review the Turing machines. There are many different kinds of Turing machine, and this figure is give you an example. You have 3 components. The first is a tape, which carry the a sequence of cells. Each cell has only 1 letter, all right? And there is a read-write head, read and write, and there is a state transition table, and it has a 5 tuple. We can consider it like sentences. I have a 5 tuple, and I get to that. And this is the state of the current machine. And given a machine and a known task, a human will program that Turing machine. Will give basically will define the input tapes and define the transition table. And for each possible input with an alphabet, and we decide which entry to enter and what's the action and what's the head motion. So you can see the input sigma and output a Q, give example, and then the control. So basically, it's a task specific. So it's a Turing machine, but the symbols are not grounded in the sense that's totally handcrafted by a human being for a particular task. So the 5 tuple we talk about is the first state, current state, and you can start as initial state as a Q0, for example, and a default state. Then this is set of input symbol. And from this tool, you go to the next state, all right? And including hard, you can hard. Then the tape alphabet, the right head can write a letter in the tape alphabet right back, all right? Then the head motion could be left, right, and stationary. So you can see that there are 1, 2, 3, 4, 5 components. 5 components completely specify the transition. This is one transition. Then you have many transitions. And when the machine hard, then the output is on the tape. And here we talk about universal Turing machine. The Turing machine we had over here is a special purpose, particularly for a particular task. What is great for a universal Turing machine is that you still have a program. That program will simulate something on the tape, but tape is not just the input, but also have 2 parts. The input is a program encoded, and the data also encoded. And the program is like that, okay? This is the transition table of that program, all right? State A with 0 input, go to state B, write 1 and write motion. State B, 0 input, go to state C, write 0, left. And all in this form, all in this form. So universal Turing machine is simulate the program on the data and output the result on the tape. So you are supposed to simulate the action of that program and simulate the program running on the data, then output the result of the program on the tape. Because the program is written by anybody. It's open-ended. And data could be provided by anybody. So that's why this is a universal Turing machine, because the program is specified by anybody else. So it's universal. But this UTM has its own program, control program. The control program, only thing it does is to simulate a program coded, running on the data also encoded. That encoding is already specified for the UTM. that UTM can simulate any program as long as coding is correct. And the data, as long as the code is correct, will write the result on the tape. So it's a universal. That's great. It's closer to what we want. It's a general purpose and open-ended. And in our new theory, we say that the tape is the real world, real world, and don't need to code it. So now the regular Turing machine and universal Turing, they do differ. And a regular Turing machine has a known task, but universal Turing machine does not have any task. Because the task is on the tape, and the data is for the task. So it's open-ended, but anytime only one task, anytime one task. So it's a general purpose, all right, they differ. And we say that the symbols are falsely grounded if you use sensors. But sensors, you send some information from the real world, but may not do it correctly because you still have a symbol. Symbol in the transition table are handcrafted. So it's not really grounded because human handcraft the symbol, and that symbol does not apply to anything other than use handcrafted. So in ImageNet, zebra type does not allow striped shirt. So in other words, that although you can have a program that recognize stripes, but you call it zebra. But if the input is a striped shirt, you still call it zebra. What's the problem? It's a handcrafted set of symbols. The symbol includes zebra, but does not have striped shirt. You see the problem? All right, so it's a falsely grounded. It's our general purpose. But any fixed set of symbol you handcrafted is a special purpose. All right. Once you design it, you will not be able to extend it automatically without you redesign it again. So, but neural network support take inputs, right? But neural network are also not grounded. Many neural networks, although they simulate how the neuron computes, but still not grounded. The neural network for computation, for example, the recurrent network for Turing machine by Harvard Siegelman. It's great in the sense that very few people simulate a Turing machine using a network, but the network input line are symbolic. For example, suppose that the input has an activation line, for example. Activation line, the activation is 1, then the input is valid, 0 is not. Then this line has only K symbols. K symbols, for example. So that's the kind of advance, but does not really solve a fundamental problem of groundedness. Still symbolic. So PSUTS is also a fundamental problem and post-selection using test set. And you train multiple networks. Each network has a particular random initial guess of the weights and a particular set of hyperparameters. And this is the one way, using machine to find the luckiest one. Another is using human to find. A human can handcraft, try many different networks and pick up the internal representation that you like, right? HMAX is like that. And Fukushima's work on IEEE transaction on system maintenance cybernetics also did that, all right? So it's a symbolic AI, and many neural networks use human to handcraft representation. And the symbolic AI is the design of a micro world. It's a handcrafted. And machine PSUTS currently many neural networks like cognition, convolution neural networks, HMAX, supporting vector machine, LTSM, and many others. And here is a table that Perceptron does not do PSUTS because it's general one network. And DN also general one. This is the only one that I know. Let me know if there are other networks that does not do PSUTS. And Purdue and Fei Li using human to select a network, and the others using machine to select the luckiest network. And this network is a theory that a control of a Turing machine is FA. And originally control is a 5-tuple, right? We designed it so that control becomes not specific for Turing machine, but FA theory can apply to Turing machine, all right? So this is the original transition table, 5-tuple, state, tape symbol, state, output tape symbol, and the head motion. And I redesigned the whole thing on this side. Did you remember we have agent FA? If all this is in the, put these 3 components into state, I cause this one to be a tape alphabet, and I cause this one to be new tape state. Then you say, hey, it won't work because this is not Q prime. But you can expand that one. You make this one Q prime, all right? So Q prime cross this one. So basically this new delta prime has a format of FA, and the difference between this and this is that you may have some don't care entries in the Q prime because you don't care of this and you don't care this, you only care Q. That's it. But still the FA, right? But you say, hey, it's kind of weird. This FA is weird because you have don't care entries. But once you have an emergent Turing machine, then we don't really need to worry about that. All right, that's the beauty of vectors. So an FA is handcrafted. Typically, there are many, many possible states. A human tries to prune many states if the goal is already known for the task given. And the microword is handcrafted as a graph. All right, and the symbolic AI will search for the solution basically, and search for the graph like Dijkstra algorithm, find the shortest path. So you have diagrams that controlled and handcrafted by as a G, handcrafted by a human, then the algorithm will search for a solution. All right, and FA is a solution for the problem in a search in the microword, and the search algorithm can use Dijkstra, A star. Difference between A star and Dijkstra, as A star use the predicted cost in the future as a cost. Dijkstra just look at the current cost from beginning to the current state. Convolution neural network, Q-learning, they are all search algorithms. And the FA, you can consider this a FA, you can consider this FA for our new definition, and they are all handcrafted. The next subject is Genesima Turing machines. So Genesima is an acronym for 8 properties. G for grounded. You directly sense from the physical world. Emergent representation. You can only have emergent representations, exclusive, no symbols. Natural representation from sensory effector. You cannot code. So this is a feature. I can feature V1 and then another type, and I call feature V2. Once you have a symbol in it, then it's not natural because you already coded use symbol. All right. So you cannot use symbol to code the features, and a feature has to be represented naturally. For example, using unsupervised learning techniques like LCA. Incremental computation, not batch algorithm, because batch is bad in the sense that it violates sensory motor recursion, and I will talk about later, all right? In other words, that the next input depends on current action. If you do big data, then you assume the action is already correct, and you cannot apply new actions. So the machine does not learn from its action, basically. It never learns from its action. And the scope closed, you cannot allow human to interfere with into the representation after it knows the tasks. Attentive, attend multiple objects, disregard the background or irrelevant distractors. Motivated, all right? Emotion is a special case of motivations. A for abstract, not just fitting data. Michael Jordan said that neural networks do not abstract well. And Marvin Minsky said that neural networks are scrappy. They didn't formulate the problem. What do they mean that they do not set abstract well? What do you mean by they are scrappy? Because they do not have a formalism to really formulate the problem. In fact, actually, if you can formulate the problem well, you already have solution actually. So formulate problem is often as hard as understand the problem and give a solution. They don't. They only talk about do not abstract well and scrappy. So it's not just fitting data, must also abstract rules. And the Genesima are all necessary for consciousness. All right, give an example that if you are not grounded, like AlphaGo, then you cannot learn like a real robot. It will not really sense directly from physical world without handcrafting symbolic representation of features. And emergent hand program is not emergent. If a hand program these symbols and these rules, humans are in the loop of symbolic school representation. Natural IBM Watson is not natural because symbol require human to handcraft, including the rules, including meanings actually. Incremental ImageNet is not incremental. It has a static set of data. So it's not sensory motor recursive, as I said earlier. Scope closed, all traditional neural networks are not scope closed. All right, like SOM, SVM, CNN, LSTM, they are all not scope closed. Given them LSTM, they need to design the gate control based on the task, right? How long the long short memory is, how long the memory should be, and how short the memory should be. Attentive. All traditional neural networks are not attentive. They will not be able to automatically select a part of input to attend. Motivated, and Q-learning is not, all right? Just function maximization approximations are not motivated like Q-learning. Q-learning is symbolic representation. And the value is not cognition-based, but rather back the error discount model, time discount model. It's a very rigid way of computing value function, which is not what the brain does. Because give example, suppose I have a PhD, right? PhD much longer. And if you think too long and you don't get to take a PhD program, that's not what our brain does, right? So it's not time discount. Time discount is very, very rigid, symbolic-based representation. Abstract, not just a function approximation, all right, on those. Emergent, hidden Y, unfolding time. So let's look at let's bridge the difference. This is the formulation extremely important for understanding brains. And because we already have a solution, I look at back, then I try to condense the key component of formulation so that you can understand, all right? Because brain is highly recurrent and it's messy, very, very messy. Without this formulation, it's difficult, extremely difficult. Like neurodynamics people, and this is neurodynamic, yeah, it's dynamic, but you don't really get the essence of the mechanism, all right? So suppose we have a symbolic transition. This is the finite-state machine, or FA. State and input, and go to next state, next input. See that I use columns, so it's a lot easier. So we can do column later on. And this is not what the traditional you see from the FA. Emergent representation, we don't do symbol. We use this original symbol become Z. So Z is a motor area, and it's a symbol, it's a vector. And the symbolic input sigma becomes a vector image. Go to next state, we use the Z, which is a motor again. Vector, vector, vector. Vector, vector, vector to replace symbol, symbol, symbol. Now you can see, hey, it's a beauty, You need a human over here to be in the loop of design those symbols. Now human is out of the loop. So the machine will output the state and will take a part of X as input, and once you get this one, you go to next. So this is only past story. The next one is more global and more correct. You need to unfold in time. Okay, we don't have a symbol unfolded in time. Do you see that? Do we have time? You don't have time. You have a symbol. This is discrete here, and also discrete into IJK. But now we need to have a time because the machine must be learning in real time. 0, 1, 2. Those are the time. You unfold the time. Then you have an area, sensory X represent input, and mode to Z represent the state, also at the action output. Then you have a hidden. Over here, do you see hidden here? You don't. So symbolic school doesn't have any internal input. And the neural network has hidden input, but they do it wrong, doing incorrectly. So once you start to be itchy, you start to interfere with internal representation, you divorce with brain. Suddenly you cannot do brain anymore. So the brain over here is hidden. You will not be able to really interfere with internal representation. Everything inside it must be unsupervised. And then this arrow means that the map from here to here, every neuron here will take input, part of input here. Every motor neuron here will take the part of input. And if you want to predict X for primate, we do not predict input on the retina, but the LGN already predicted. So basically that for lower animals, they do. All right, normal animal that has a projection from central nervous system into the retina for lower animal because they don't have many neurons. And then you unfolding time, you can see that once you do that, it's a partial connection, not fully connected. I will get to that later, how you can do cost to find approximation so that cost to find approximation will do a reasonable job with this time complexity. And the unfolding time is that, give examples, this one can go up, right? And go down again, you see that? And go up and down means a highly recurrent. But if without time, you really get confused because highly recurrent network like that, it's really hard to understand and analyze. Unfolding time, key. Then you can model the whole Holy Grail complex problem using mathematics. That's how this formulation is a key to understand. Then we have a brain model. Of course, there are many techniques that are biologically informed. Then you have a holistic solution by putting to this biological measurement together to get in the model. But this formulation is one of the key for understanding. Then a little bit more. I want to, this one did not relate the word. I want to relate the word. You consider sensible word W prime, then sensor X, which is here, and the space of the sensory input. Then scald brain closed Y here. Then you motor Z. Z can be you said active word. Do you see that? Over here I have 0, 1, 2 as a time. I have another column row, which is 0, 1, 2 time. And see that this is unfolded time. So identified for APFGP in the end. And you can see that how the brain, this is the brain part, sensor, motor, and hidden area that interact with the word. And the word, this word may not be exactly the same. And you can see this part, you can activate this part, but you may not be able to see some of this part, for example, like my back here, right now you cannot see. And you never see something inside your tummy, for example, right? So it's there, but you will not be able to see that. And this is the active word. I can act on the screen, I can act on this mouse, but does not mean that I can act on everything, all right? And this is unfolding time. So now let's understand how DM for universal Turing machine. I give this a kind of very intuitive diagram to compare with symbolic network, like this one. This is a hidden mapper model. Also many neural networks like that. So even you have image as input ABC, and once you have ABC as this is emergent, but once you have label, so this is feature A, feature B, feature C, then you have a hidden Markov model, for example, right? Then you have a symbolic input. These symbols are killer. These symbols are killers. They would not allow the input to go beyond this. This is a static definition of ABC features. And then you have input that will not fit this ABC. Then the system breaks. Then hopeless. Alpha, beta, gamma is the state. And this is like unfolding. We see that the way I do it, I try to like unfolding in time, but still unfolding time not sufficient because this transition is not the typical way you see the how finite state machine learns, right? Alpha, beta, gamma is input. In this case, alpha with A, you go to alpha, you have a C, you go to delta. So this is FA, but you do not see typically write this way. I write this way so that you can understand this. This is that you don't have alpha, beta, gamma as a symbol, but rather you have a image and each pattern here corresponding to a state. So we have huge numbers states, and a neuron will do interpolation. This is beauty. And unfolding time, this is 0, 1, 2. I used 0 did not write here because if to satisfy this transition, you need 2 times ticks. I explained to you why. You need to get X in and Z in, then you have input Y that compete. You have 6 neurons here, and is the top one computation. Suppose this is the matched best. This neuron has a global Z input and match this pattern, and it is a global input here. But this neuron have local input, and different neurons have different feature, different locations. Because they have different location, different features. So if you have many neurons, then you have many local features. Then once this neuron compete with that, competition number 1 now. If we don't have competition like error back up, then they will use the gradient. And gradient, you want, you connect me, you help me, but it's not his job. You should not ask him to help you. So gradient give a wrong demand to the wrong neuron. Over here, it's competition. I compete the best means that I'm best for this job because the match has to have a top-down input. This pattern with this input, I'm the best, and this pattern, this is I'm the best, and I'm the best job, and I should be updated. You guys should keep shut. Keep shut. Don't change. This is my job. Then I fire. Then once I fire, and this learning is by heavy learning. This is heavy learning. And this is also heavy learning. The motor, this motor could be self-practiced or taught. For sensory motor learning is taught by human being, but for imitation, it's generated by the network itself as trial and error. And once this neuron fire, you see that suppose I'm doing practice, right? This neuron fire, this neuron fire, this neuron fire, and this is the pre-synaptic neuron, post-synaptic neuron, and heavy learning will link this one. You get LCA later and get to the detail. So wiring is automatic, and later on you will see that this wiring is probability. Probability of frequency for this neuron to fire, condition on this neuron fired. This is a probability, and that's why optimality is established. Then this neuron fire, this becomes the context for this neuron. So you can see they have 2 circles, this one and this one. So for the input and Z to go through hidden neuron and go to this again. So that's why you have 2 circles. So it does have a cost, all right? You have internal representation, it does have a cost. You slow down the time clock, okay? And then what happened, you have attention. So if this neuron learned local representation, if computation is such that, for example, suppose this is the context, right? This context means that you should pay attention to this one. And this context means you should pay attention to this. This context means you should pay attention to this. Do you see that? So the context really tell you the attention. Then if this win attend this one and this lost, so they did not pay attention to the global view here. And if this win, you pay attention to this location, and same location may have different features. You may have a not just location attention, but also have feature attention to detect objects, right? And so that's the idea of a universal Turing machine, because when you learn from the viewer may not be just the data. It also could be rules. If we have abstraction, I will talk about it, you learn rules. So rule and the data in this case are unified, same thing. I get to that. So vision is hard. I give you an example. Suppose we use symbol to represent what do we mean, all right? So you can understand. But once we have emergent representation, we don't need a symbol anymore, all right? So look very complex word, right? And suppose I'm navigation, and I want to avoid this one, right? And simple for child, because child has emergent representation in the brain. And for DN, it's also symbol, because it's just learning a number crunching, right? Law will emerge. So they could have this concept like action, GPS, what where scale of the object, right? And then you have symbol to represent the meanings. Then this is the context, this is the input, the win, win. Then you have this context, this will win. And this one, this context, this, now you pay attention to locally, this win and link to this. With this context, they continue on. So sometimes you pay attention to local, you sometimes to global. And later on, you can pay attention to this and so on. You can see that it's just mechanical way, but the behavior looks very, very complex. Behavior is very, very complex. Then how does do segmentation, right? We see that, suppose I have I want to segment this one. How do I do segmentation? And in fact, each neuron does that, right? The neuron does not need to be a receptive field like that. You may start from circle, give them, but later on you trim. I'll talk about synapse maintenance later. This is the idea of synapse maintenance, actually. You start with a square, then this is the compass object, then you have background, you have object. And because when you find background is random or pseudo-random, but once I match, I matched this one well. So these neurons will not, this synapse will not match very well because the background may change, right? Background will change once I fired. Once I fired, open my eye, I sometimes see this, sometimes see other things. So the deviation of the background is high, and I will cut. This is the actual mask of the object. This is the neurons receptive field starting from square. Now it becomes complex shape because those areas are cut. The black areas are cut. And there are some still some totally cut signal inputs and weights, and will be gradually will cut. The more you learn, the better. The more you learn, the better. So you can see that neuron will automatically doing segmentation based on statistics, not based on supervision. And this example, how you deal with the foreground background. Over here, you have the foreground and this object also foreground. But because the foreground may change, this is that, and the object attended may not change, and it's stable for this particular neuron. And we look at this pattern, then the trim will cut off the background, and you can have a different size and different contour. So in general, it's general, and deal with multiple objects. in this case, hand and object, right? And different background and different scales in this case. So developmental network, we explain the brain. I will give you some early example where you have a context. This X, Y, Z as a context. That's T minus 1. Then I have a T and T plus 1. And the transition like T minus 1, T plus 1 is the unfolding time. And each Y neuron has input from X and input from Z. That's two, this is sensory receptive field and motor receptive field. And also as a lateral input, I'll get to the lateral input. Lateral input is like you have higher order Markov field and allow you to do thinking, allow you to pay attention to this internal response, basically. Then you have a left receptive field, a lateral effective field. You have lateral receptive field, lateral effective field. And this neuron will take this input, and this neuron is your effective field. This neuron takes this your input, and this in the effective field. This neuron take the top-down input, this is the centrally effective field. See that totally that you have 6 fields concepts, right? And if you do that, given up I have a background, you have an object APFGP in this case, then the occipital lobe will have features that has each feature has 2 components: sensory components and top-down inputs. Given up, this one has a top type A as a context, motor concept, and this pattern of A, and so the color corresponding to the object A, and blue corresponding to object B, and the connection top down from the motor A and B types. So each neuron, because it handles the context, has 2 components: the sensory input and the motor input, top down and bottom up. Then you have other areas. We have now parietal area. Parietal area is more related to motion. So give example, location. So we have high and hand pointing, right? Pointing is up left, up right, lower left or lower right. So this is the muscle that pointing. So this one is more related to the location. And the temporal lobe, over here, it's more like temporal lobe is more related to our vocal tract. So then you can have a meaning, and a meaning into the higher rules, for example, that give you this one is going to have a more type like, and here is more location like. And you can see that the later area is more abstract, and early area is more sensory. More sensory means more concrete. More motor means more, how do I? Abstract. More abstract, more concrete. More abstract, more concrete. So that's how the representation in the huge brain are automatically formed based on the local features, because globally, originally you may have a global feature, gradually you define the connection pattern, the neuron becomes, some neuron are global connections, some neuron are local connections, just like the model like we had here, right? Some neuron has a global connections and some neuron has local connections. So that will emerge automatically, like here. And you further on, not just object, location type, and also could be locate a relationship, right? So have a agent A, B group, A play B, A give B to C, those are the relations, right? And this can be like a pair in this case, right? And this can happen, I draw another C. Suppose I have a neuron that has input from location and from type, then this neuron becomes, you have 2 locations and 2 types, then A, B, 2 types, 2 location and B, then this neuron become relation between A and B. So AB is a relation, do you see that? So originally, you have only wing-headed neuron, but I unfolded so that these multiple top-down inputs as folded out, you can see that automatically form the relations. But actually the hidden area will have this area and this area in the same skull. Same skull. It depends on connection. They may have different meanings. So now I like to introduce some developmental network DN theorems. And if you're interested, you can look at the proof. First, the controller of Turing machine is FA. DN is the emerging controller of a Turing machine because it learns any FA. DN is optimal in learning any DN and any Turing machine. If we have a sufficient number of hidden neurons, then it could be error-free. By the way, any Turing machine is a finite. So if you have enough finite number of neurons, then it's learning error-free. But in the real world, but it's open-ended, right? You go around, you live on, and the number of inputs will be more than the number of neurons you have, all right, very quickly, and you do not have sufficient neurons. Then we already proved that it's optimal in the maximum likelihood. So basically, there's no local minimum out here. All the neurons that's optimal given the number of resources. And emergent Turing machines are logically complete. Like a universal Turing machine, in principle, a network can learn any program from the real world and execute the program. And the emergent Turing machine with motivation, once you have a general purpose, right, and how it motivates itself, you really need to have a motivation that it can automatically program. Once you have a motivated Turing machine, then it can program itself based on its motivation. And the DN is a control of a Genesima Turing machine. I give you some formulation here. FA is symbol, go to next symbol. State, input, next state. Then it becomes motor vector, sensory vector, go to motor vector. Then we have a symbolic search using neural network. Competition is like search. So it have a top-down input, top-down weight, bottom-up input, bottom-up weight. Then you have a simplistic version, you have a two energy add together. VT, VB. VT is the inner product of the two unified vectors, T and Z. Two unified bottom-up vector and X. And this maximum is 1, minimum -1. Maximum 1, minimum 1. So the maximum is 2 in this case. Then you do search. If you do Turing machine alone, then you probably can think about search is IJ. I is row and J is column, for example, right? And then you can search all the inputs and to find the max input and you find which row and column matches, right? And I use the vector to represent the corresponding IJ. See that? So it's originally don't have row and column, but in order to match our DN to the Turing machine, you can use IJ as the index, all right? Real world does not have IJ actually, infinite many images, infinite many motors, but now we look at IJ, so it's easier to understand. You search for IJ, you can learn Turing machines using DN. So why not handcrafted features? I'll give you an example. This is a big data from George Coates. He's doing very well, actually, comma system for lane centering. And those are the features. And the features are the, I think, he didn't say much about in his talk, but I think that's the ages, all right? And I think that he will do age groupings using neural networks. And but once you use ages, right, you will not be able to really extend it to other features. For example, that I picked my wife from airport. We have snow on the road, and as soon as they have a snow patches that cover the land, and the camera does not have the landmark on the screen anymore because it will not be able to detect lanes at all. As soon as the lane appeared, the marker on the lanes will reappear. So that's indication that it did not estimate the lane based on snow patches, for example. It wouldn't do that. So it's brittle in that sense, right? Brittle. Now, error back pop, competition, I get to that, all right? So suppose I have an input, but I have many input. I took these images from ImageNet so that I can explain the weakness of ImageNet, all right? Suppose I have an ImageNet inputs like that. Then I have a bird, cat, and dog. That's the class that ImageNet use symbols. And I don't have enough neurons, right? And in this case, I have 6. Over here, you have 12. You have 12 patches. I have 6 neurons. Then you really need to win. You suppose you have a competition, then this neuron maybe shares this one, and this neuron has this one, and they start to do cluster. Without competition, you will not be able to do cluster. So without competition, error backprop is like Mao Zedong. Chairman Mao Zedong in China, and he wants to really reduce the error, for example, then we will say, you connect me, you can help me. You help me. But in this case, this is 4 neurons. Some of the input are not their job, but just connected to you for my job. I connect to you. You want me to help you for this? That's not my job, for example, right? You don't possess this neuron and did not really take care of this job, but Mao Zedong wants this one to help this job. See that the problem? Mao Zedong wants this neuron to handle this job. Then it messed up. They don't know what they do, right? This guy will not do everything. This guy will do everything. Mao Zedong wants me to help everything, and based on the connections weight. Connection weight is my confidence to you, not for this case. It's like math, right? It's math. So Hinton 60 million parameters use post-selection because there's no way to do that. You must have a very lucky initial weight assumption so that you have a smaller mass. It's still mass, but smaller mass. And it's critical to have a very lucky weight assignment. So Chairman Mao is lucky. Chairman Mao maybe do many cultural revolutions. Maybe certain cultural revolution was a kind of lucky, so that the damage is relatively less. It's the luckiest revolution. Genesima universal Turing machine theorem said that DN autonomously learn any Turing machines, including universal Turing machine, because universal Turing machine is just, you don't need to change definition. It's only the transition function different. And universal Turing machine is a Turing machine to generate a grand Genesima universal Turing machine inside it with the following 2 properties. First, if you have a sufficient neuron, it's error-free. If you don't have a sufficient neuron, then it's optimal in a maximum likelihood sense. So in that sense, it's optimal. It's optimal. So solve the local minima problem. Let's look at the performance difference. People said, I don't care about biology or not. I just want to in engineering problems. And if engineering problem, it's intractable and the data becomes illusion. I'll give you an example. We have this particular is a vision problem, and because the optimal, our DN 2 version, this learning concept where and what, and this doesn't. It just without teaching and learning where what. So otherwise, there's no sub concept to be learned. Here is the GPS. That's with recognition learning where and what. But this is CN, this is CN, this is DN. And go through the data, all the data, 10 epochs, 10 times. The error is still, this is the luckiest network, all right? And many garbage network we did not even see. With the luckiest network, even luckiest network did not do as well as DN. Then he started, this is the 10 epochs. So let's do 10, 10, 20, 30, and 100, 200, 300, 400. And even the 500 is still much higher than our network. This is much higher than our network. This is the luckiest network. So you can see that our network is much, much better. First epoch already reached minimum. 500 epochs, the luckiest network did not really reach the minimum.